Okay. So yeah, we'll leave that open for a little while, the attendance poll, and we'll get started with today's lecture content. Okay, so we're covering rejection sampling. Hang on, I feel like I'm just a tiny bit too loud. Okay, is this still okay? Can you guys can still hear me, right? Okay. So we are doing rejection sampling, and on Friday, we covered the uniform case where we had a uniform proposal distribution. Okay. And we said the PDF, our desired PDF, is going to be proportional to sine of x, okay? Or in other words, f of x is equal to some constant times sine of x, and x is on the interval 0 to pi. Okay, so thus our PDF looks like this. It's the sine function from 0 to pi. And in order for it to be a PDF, this whole thing has to integrate to 1. So we integrate 0 to pi. If I integrate 0 to pi of sine of x dx, then what we will get is negative cosine of x from 0 to pi. And this thing will equal 2. And thus, c has to be 1/2, giving f of x is equal to 1/2 sine of x. This is our PDF. Okay, so this is our PDF of the target distribution. Is that okay? And we said our proposal distribution is the uniform distribution from 0 to pi. Okay. And so if the proposal distribution is uniform from 0 to pi, our g of x is going to be, what is it going to be? It's going to be 1 over pi for 0, for x between 0 and pi, and it's 0 elsewhere. Let me just all right. Is that okay? And what we're going to do is when we graph this, we are going to multiply. We multiply g of x by m so that m times g of x is always bigger than f of x for all x. Okay, and so what that will look like is we'll get a rectangle like this. And you know what is the height here? Should have a height of 1/2, right? So, is this picture okay? Okay, so our desired PDF is proportional to the sine function. It's 1/2 times sine of x. And then our proposal distribution is going to be the uniform from 0 to pi. Okay? And so when we look at our diagram, we've got to figure out m. Okay? So if we have f of x equal to 1/2 sine of x, the max value of f is what? Is 1/2, right? Okay. And meanwhile, g of x is equal to 1 over pi. So if we want m times g of x to be greater than f of x for all x, what should m be? M should be pi over 2, right? Because then m times g of x will be pi over 2 times 1 over pi, which will equal 1 over 2 for all, and this is just which is greater than or equal to f of x for all x. For all x between 0 and pi. Okay. So the blue line, this is going to be m times g of x, which is effectively 1/2. Okay. Okay, and so the rejection sampling works like this. Okay, so it says first we will propose x drawn from g of x. Okay, so in our case, that's the uniform 0 to pi. And then we will generate u, and then we accept x if u is less than or equal to f of x divided by m times g of x. Okay, and you reject it otherwise. And that's rejection sampling. So we have our target PDF, which in this case is 1/2 sine of x. And and we would use rejection sampling generally if inverse CDF method is difficult or something. In this case, we have such a simple PDF that inverse CDF is not hard. Okay, right? It's very easy to do this. But this is more an illustrative example. So we're going to pretend like we can't do inverse CDF for 1/2 sine of x or something. And so we generate a value between 0 and pi from the uniform distribution. The uniform distribution, though, will propose all values on that interval equally. Okay, values near 0 are proposed equally as values near pi half, which are proposed as equally as values near pi. But if we look at the PDF, we don't want all the values equally, and we want to reduce how many values we have near 0 and how many values we have near pi. And so we use the u and kind of our this rule of whether we should accept it or not, and this will throw away some of the values we propose, but the resulting sample that we have after we've rejected some of them will follow the PDF that we want. Okay. And so this weekend I spent some time making these animations on my computer, okay, to try to illustrate. R actually there's a package called animation, and it's kind of fun. All right, I gotta say, I mean, this is this is what I do for fun. I know you've heard me say it so many times, but I really love my job, and like I had fun making these animations, and I hope, let's see, I hope the animations are useful in helping you understand these concepts here. Okay, so let me kind of. All right, so this is our PDF that we want, okay? And this is the regular, this is our proposal PDF, okay? But so the proposal is equal to 1 over pi here, okay? But we see that it dips below, so what we have to do is I'm gonna find kind of this ratio, which we've found to be pi over 2, and so let me just show you what this will look like if we do this. This is what it looks like. Okay, so after we multiply pi over 2 times our m, and actually here it goes up to 1 to kind of illustrate that it goes from 0 to 1 for the ratio. Okay, so here I'm going to let me run this animation here. Okay, and we'll go ahead and generate this thing. And oh, okay, so all right, it's running here. Let me I'm gonna go ahead and close this poll thing. All right, so let me just kind of go cycle by cycle. All right, so in the beginning, this vertical line represents a value of x between 0 and pi that it's proposing. So here it's proposing a value like 0.9, okay? So it proposes that value, and then we generate a value between 0 and 1, okay? So the real graph goes from 0 to 1/2, but basically to kind of show 1/2 is now the new 1, basically I just multiplied everything by 2 here, okay? So we're gonna propose a value between 0 and 1, and we're proposing this value like 0.38 or something, okay? And if it's below the curve, we will accept it. So we accept it, and we get a little green dot here, okay? And then we propose a new value between 0 and pi with equal probability. Here we're proposing a value like, what is this, 1.8, okay? And we're going to sample a value between 0 and 1. So we're sampling like 0.9-ish, okay? That's below the curve, so we will accept it. Here's another value around 0.7. Okay, we propose a value. This value proposed is like we sample a value u. This is above the curve, so we're going to reject this value. This value just gets thrown away. So we spent a little bit of computational energy getting this random sample, but it just gets thrown away. It will not appear in our saved sample at the end of the day. And we just continue. Okay, so here we're proposing a value near 3, like 2.95. This is the sample u that we get, and so we will reject that, okay? And so I'll just let this run, and so it just goes from propose, sample, accept, propose, sample, reject, or whatever it might be, okay? So if it ends up above or below the line, you will either reject it. Here we'll accept it. We accept, and I don't know if it's obvious, but being a uniform sampler, all values between 0 and pi are proposed with equal probability. Okay. All right. So does this animation kind of make sense as to how the thing is working? And so I just wanted to also kind of illustrate that being the uniform sampler, this is just to show the values that are being proposed, and we can see that values between 0 and pi, all of those values are kind of showing being proposed with equal probability. So the whole thing is, we're getting lines all over the place here, okay? Okay, let me just also show you. So in this thing that I ran, I think I ended up just having a total of 20 points sampled, okay? And so you can see the ones that are under the curve get accepted, the ones outside of it get rejected. I can do this a little bit without the animation. I can do something like 10,000, okay? And we can see that this is the resulting histogram, and if I compare the resulting histogram of 10,000 points to the PDF, it follows the PDF quite nicely, of course not perfectly. And then if I were to just kind of plot them all, this is just I think 1,000 here. We can see, you know, quite a few points. You know, it follows the thing there. Okay. Let me also. I just want to kind of. Where did my code go? Okay, and so just to also further illustrate this, I just want to take like 2 tiny little slices and just kind of show what happens inside these slices. So here is a slice going from 0.2 to 0.22, and I'm going to zoom in kind of on this window here, okay? And so if I zoom in just really here and just kind of zoom in and stretch this out, the resulting plot will look like this. So you can see I'm zooming in onto kind of that 0.2 to 0.22, and here I sampled a total of 10,000 points, and I said how many of them fell in between 0.2 and 0.22, and we got something like 68 of them fell in there. Okay, and here I'll just generate some random values between 0 and 1, and of these, how many do we accept and how many do we reject? We can see we will accept any of them that fall below the PDF, and we reject all the ones that are above. Okay, so we reject quite a few, and we accept, you know, not that many. If I go back, then we'll zoom in on this one. This is near 1.1, and the PDF is up here, and so we'll zoom in just on this this interval right here. And so you can see kind of the PDF runs closer to 0.8, 0.9-ish. Okay, and we ask, and these were, of the 10,000 values, these are the values that fell in between 1.1 and 1.2. And again, we just randomly sample values between 0 and 1. And those that fall below the line will be accepted. Those that are above get rejected. Okay, and so here we're accepting most of our points and we're rejecting far fewer. And so if we just go back to the original, and now I'll zoom out and just plot those sets of points again. So these are those same values. Okay, we can see these ones got accepted and these ones got rejected, whereas these ones are accepted and these ones are rejected. Okay, and so we can see that even though values near 0.2 are proposed just as frequently, only a small handful are being accepted, and values that are proposed near 1.1 are proposed just as frequently, but they are accepted far more often. And thus, when the resulting sample will follow the PDF as appropriate, because we're proposing a bunch, but we're not accepting all of them when we're not when there's fewer values. Okay, and so if I just kind of plot kind of all of our points, you know, this is just all right. It looks like that. Okay. So that's the uniform case for rejection sampling. And before I move on, I just want to make sure, see if anybody has any questions about this. Yes.
For choosing M,
Why
can't we just choose an absurdly high number?
So if we choose an absurdly high number, that's valid. It will work. But what will happen here? Let me just kind of show you what would happen if I said M is equal to like 50, right? What would happen? Then, so I'll come back up here and I'll just say M is 50, because I don't feel like doing the math to figure out what's the ratio I should be using. Okay, so here I'm going to say m is 50, and when I plot this, what we see is okay, so I have to redo this. My y limits should be 0 to 1. Okay. I don't know. Okay, so this is what it looks like, and basically, I'm only going to accept if my u ends up below the curve. Okay, so in the long run, it'll work. Okay, in the long run, it'll work. But what's happening is 99% of the values I propose are going to be rejected. Okay, and so that's the problem with using just an m that's way too big. You can, and it'll work. And it's like, if you couldn't figure out the math, just say, I don't know, let's go, big M. And in the long run, it will work, right? If you have infinite time, yes, everything works. But we don't really have that much time. So using a big M will lead to a very low rejection rate, and we don't want that, okay? Okay. Any other questions? And so yeah, the best value of m is going to be the one where you end up kind of being tangential to the thing, like this. Okay. Okay. All right. Well, if we are good with the uniform proposal case, then we will move on to rejection sampling the general case. Okay. General case. Okay, and we would do the general case. Let's say the PDF of our target distribution extends to infinity. Okay, so let's say your PDF of the target distribution may extend to infinity. All right. So in that case, we cannot use the uniform distribution as a proposal, right? So we cannot use, why can't we use the uniform? To propose values. Because your g of x would be 1 over infinity, okay? And it's just not possible to propose values on that interval, okay? So, uniform, either whether it's from negative infinity to infinity or uniform 0 to infinity or whatever it might be, you're going to have a g of x of 1 over infinity, and you can't use that to propose values. Okay, so this is not going to work. So the proposal PDF itself also needs to extend to infinity, have the kind of the same domain. Okay. Proposal PDF. And the general case is just basically the proposal PDF is not the uniform, and it's probably, it's very applicable in cases where things go to infinity and you have to use something else. But you can also have a closed interval thing. But this is what we have. Okay, the big idea for rejection sampling is exactly the same. All right. Okay, in that we have a target PDF f of x. Okay, and we will and we're doing this because this PDF is, we'll say, is this is hard to sample from directly. And then we have proposal PDF G, which is easy to sample from. Okay, and the process goes like this. Propose x from g of x. All right, no problem there. Okay, and again, we have some value m so that m times g of x is greater than or equal to f of x for all x. And then we generate u from 0 to 1. And then if u is less than or equal to f of x divided by m times g of x, accept x, otherwise reject it. Okay? So the concept here is exactly the same as the uniform case. The only thing that's different is that in the uniform case, the PDF of the proposal, g of x, is a constant, right? In our case, it was like 1 over pi, or if you have a different interval, it's going to be 1 over some constant, okay? The 1 over the width of your interval. So in the uniform case, g of x is a constant. In this generalized case, g of x is now a function of x and is not going to be constant. And thus, finding m becomes a little bit trickier, because now you have to find the value m to make sure that this ratio f of x divided by m g of x is always less than or equal to 1. Okay. All right. Is this okay? So let me do. We're going to do an example here, and so in our case, we're going to have our target PDF to be the folded normal distribution. Okay, so the normal distribution looks like this. It's supposed to look like that, okay? Or my thing is supposed to look like the normal. And the PDF for the standard normal is 1 over root 2 pi e to the negative z squared over 2. Okay, so that's and z is on the interval negative infinity to infinity. Okay, so that's the normal PDF. And the folded normal is basically the exact same thing as the normal, except it's only positive. So the folded normal looks like this. Okay, so this is just the positive half. Okay, and so f of x in this case, because it's basically exactly the same as this, but because it's only half and it still needs to integrate to 1, it's going to be twice as tall. Is that all right? So it's going to be 2 times 1 over root 2 pi times e to the negative x squared over 2. Okay, so it has the exact same PDF, but it's twice as tall because it still needs to integrate to 1 in order to be a PDF. And in this case, x is on the interval from 0 to positive infinity. So that's what we have. Is that okay? And we're doing the folded normal rather than the normal because the folded normal goes from 0 to infinity, and we have another distribution that goes from 0 to infinity that's very easy to sample from using the inverse CDF method. Okay, and so our proposal distribution is going to be the exponential distribution with lambda equal to 1. Okay, so the proposal distribution will be exponential with lambda equal to 1. And so g of x has density lambda times e to the negative lambda x, which in this case with lambda equal to 1 is just e to the negative x. And its PDF looks something like this. Okay, it's really hard to draw this. Okay, but I think you know what I'm trying to draw, right? So this is e to the negative x, g of x. It's e to the negative x, and this goes from 0 to infinity. Okay. So this is our proposal distribution. Is this okay? And sampling inverse CDF is basically, for this case, so our inverse CDF is going to be sample u, and then x will be equal to negative log of u, right? That's inverse CDF. So this is very easy for us to do, to get random values from the exponential distribution. Okay, so let me just draw this. Okay, so if I so here is the exponential distribution. And there is the folded normal PDF. Okay, and so, well, I can't just go directly with the exponential distribution and the folded normal because the folded normal is taller than the exponential distribution in some locations. And so what I need to do is I need to multiply the exponential PDF by some constant m so that it is always taller than the PDF of my target distribution. Okay, so basically I'm going to find where this is most tall compared to this. Okay, and so I need to find basically the maximum value between the ratio of my target PDF and the exponential. Okay, and when I do that and I plot it accordingly, then I would get something like this. Okay, so that all I did was I just multiplied the exponential distribution by a constant. So I went from here, I just multiplied this by a constant so that it ends up being taller, and thus it's always taller than my target PDF. So my target PDF remains the same, but now I've made my exponential distribution taller. Okay, and so the math for that, requires a little bit of work. Okay, so our target has f of x equal to 2 times 1 over root 2 pi e to the negative x squared over 2. And proposal g of x has PDF e to the negative x. Okay, and so what we want is we want an m which is going to be bigger than the maximum value between f of x over g of x. Okay, so where is f of x largest in comparison to g of x? We'll just take that, and whatever that constant is, we're going to use that to multiply it by, we'll multiply g of x by this value so that it ends up being always equal. Okay, so this is going to be equal to the maximum value of x, and we just do 2 times 1 over root 2 pi times e to the negative x squared over 2 divided by e to the negative x. Okay, and so this ends up being, we want to find the maximum value of x of basically 2 times 1 over root 2 pi, and then you combine exponents, and so you'll get negative e to the negative x squared over 2 minus x. Okay, so that's what we have there. And basically, the x that maximizes this function will be the x, because it's e raised to this negative exponent, will be the x that minimizes the quantity x squared over 2 minus x. Make sense? Okay, and then so that's easy. We just do take the derivative d dx of x squared over 2 minus x, and I get x minus 1, and so x is equal to 1. That will be the value, and I plug that in, okay? And so m is going to be greater than or equal to 2 times 1 over root 2 pi e to the negative 1/2 minus 1, and that will give us something around 1.32, something around there. Okay. It's easy to do this in R. You just take. You guys get this written down? Okay. So in R, all I have to do is just do PDF over the interval divided by G of S. Say ignore any NAs and give me the max value, and here the max value I get is 1.32, 1.315. All right, so anyway, I plot this thing. This is what it looks like. I should add a title. Something wrong. Okay, never mind. Don't mess with. Okay, I don't know what to do. All right, so I'm going to run the animation here, and oh, okay. So first, this animation is to show with the exponential sampling. You're going to see that because the PDF for the exponential distribution is tallest to near 0, it's going to propose values near 0 a lot more frequently, and so this area ends up getting a lot of lines, and values out over here are sampled a lot less frequently, okay? Because we're no longer sampling from the uniform where all values are equally likely. Here we're sampling from the exponential, so values near 0 are most commonly sampled, and values further away are less commonly sampled. So that's what this animation is supposed to show. And then run this, and I think, So here is our here. So okay, so let me just rewind here. And so here I randomly sampled a value, okay, and it's like 1 point something. And then again, we're going to sample a value. This shouldn't say ratio anymore. A value between 0 and 1. And so now a 1 means the value is at the top, at the blue line, okay? And so we get something, you know, I don't know, this looks like 40% of the way up to the blue line. So it'll be there. It's under the curve, so we will accept it, okay? Here I propose another value, and if I sample 1, it means it's at the blue line, and anything else is somewhere lower. Oh, that's like very close, and I can't tell if it's above or below the line, and apparently it was above, and so we reject it, okay? Here's another value that's proposed. It gets rejected, okay? And here's another value that's proposed, okay? And in this case, again, it gets rejected. And I'll let this run, and what we should see is that values near 0 are going to be proposed a little bit more often, okay? And whether we accept it or not depends on whether that U value ends up being above or below the curve, okay? So I'll just let it run, and you can kind of see, you know, if the U ends up being below, we'll accept it, and so, you know, again, it's cycling through propose, sample, accept, or propose, sample, reject. Does that kind of make sense? And so I'm hoping you're kind of seeing that values near here are proposed indeed more often, but whether they get accepted or not, again, depends on whether that U falls above or below the curve, okay? And if it falls, so even though these values are proposed a lot more frequently, because there's a larger gap here, they're not accepted as frequently. And then every now and then we'll still get values proposed way out here, and you know, I stopped drawing the curve at like 3.5, but you know, we can still get values way out here. All right, I don't know. Does this make sense? This animation? Yes. Question.
So you're drawing when you're doing the sample for the uniform distribution, it's from 0 to the top of the exponential distribution at that x value.
Yes, it's to the top of that exponential distribution at that x value. Yeah, and so 1 means it's at that line, and then everything is kind of you know, scaled out from there. Okay, so this word ratio, I'll have to fix that. It's not actually the ratio. Okay, all right. I don't know. Are these animations kind of cool? It was fun. I had fun making them. All right. And then so in that case, I think I did like 50 values, and let me just kind of plot the ones. These are the kind of the 50 values that we proposed, and we show which ones we accepted and rejected. Okay. And so these ones got rejected, and these ones out here get rejected. So the exponential distribution also goes out to infinity, but because you know, the normal distribution drops off a lot faster, because the normal is basically e to the negative x squared, and the exponential is just e to the negative x. So it drops off. It drops off faster. And let me just show you what happens. So here, if I do the same thing but with like 10,000 samples, okay, and you can see I'm only using RUnif, and to get my exponential, I'm just taking the negative log of that uniform sample. And I'll run this. And so this is with, you know, kind of like 1,000 points drawn from here. And so you can see the proposed points all, you know, follow the exponential, but the ones that accepted follow the normal PDF, at least the folded half. Okay, and if I draw a histogram of the resulting of the sampled points, so these are the proposed points. The histogram of the sampled points follows the exponential, and it goes, you know, we don't have very many out at 8, but we do. Whereas the histogram of the normal PDF follows the normal distribution quite closely. Okay, and in order to go from the normal PDF, the folded normal to the regular normal, because the normal is symmetric, we can take advantage of that, and we just say, all right, we got so here we get a random point from the folded normal, and then all we do is we flip a coin with probability 0.5 and decide whether it's going to be a positive or a negative value. Okay, and if you do that for every single point, overall about half of your points will be negative, half of your points will be positive, and the result will be a true normal distribution. Okay, and you guys have to do this in your homework. I pretty much did the homework here. I've tried to obscure some of the code, but basically you're going to do the same thing. Obviously, if you want to do the animation, you can look up on using the animation package, but that's not part of the assignment. You're going to basically generate samples from the normal distribution, which is a difficult thing to do. We don't have an inverse CDF method for it, and so this is one way for us to get normally distributed samples by rejection sampling here. Okay, we'll end here. We'll see you guys on Wednesday.